Hello. Now we'll discuss regarding the design of levers. Okay. Now, what do you mean by the lever? Okay. How the components of the levers will be designed. Okay. That we'll study step by step. Now let us see. Uh, this one type of lever we have seen, that is the different components of the levers will be. It is a fulcrum. Okay, these are the arms, this is the load, and this is the effort. Okay, now applying these efforts, okay, with the help of a fulcrum, at this point this load will be lifted. Therefore, a lever is defined as a mechanical device in the form of a rigid bar pivoted about the fulcrum to multiply or to transfer the force. For example, we want to remove a nail from the wall. Now to remove it directly, it requires certain more amount of force, but if you are using this type of lever where it is being supported at the fulcrum means it is a support. Okay, we are going to apply the effort, fulcrum will be supported, and easily the nail will be removed. Similarly for the scissor also. Okay, now we are applying a load. Okay, this is the load is there, this is the effort arms are there. Now using the fulcrum at the effort arm, okay, we are applying the forces at the effort, and automatically the what are the operations are to be carried out by the scissor, that will be completed. Therefore, the major components of the lever is nothing but a load, effort, and the fulcrum. Effort which is to be applied, load is to be lifted, and the fulcrum is nothing but your support. This is the effort arm and this is our load arm. Now let us see one more example for this pictorial example. That is the effort arm, fulcrum, and the load is there. This is one of the gripper is there. Now this is one most popular example of our childhood, that is we are going to play with the seesaw. Okay, where input force will be there, output force will be there, and this is the fulcrum is there on which it is being supported. Okay, this is also called as a fulcrum and the levers. Okay, now we'll see some of the definitions. That is the load, it is generally denoted as F. It is the force produced by the lever. It is the force to be lifted by the lever. It is the force which is to be produced by the lever. Then effort, it is the effort required to lift the load. It is the efforts are input and load is nothing but your output. Therefore, the mechanical advantage will be calculated as load divided by effort, that is equal to F by P. Then the leverage is equal to effort arm divided by the load arm. Effort arm divided by the load arm, that is nothing but L1 divided by L2. Now let us say simplified diagram. This is the load, this is the effort. Okay, this is the effort arm and this is the load arm, and it is being supported at the fulcrum. Therefore F into L2 is equal to P into L1. Therefore you will get F by P is equal to L1 by L2. Now F by P is nothing but a mechanical advantage is equal to the leverage. Okay, now we'll see the different cases of the lever. 3 different cases of the levers are available. Now first case of the lever, first case where the mechanical advantage is greater than 1. Now let us, what is the mechanical advantage? Mechanical advantage, load divided by effort, that is F by P. F is greater than P, then mechanical advantage will be greater than 1. Okay, now this is a load, this is the effort is P, this is a load, this is the effort arm and this is our load arm. Now L1 is greater than L2, F is greater than P. Okay, therefore what will happen, you require more force at this location. Okay, you require more force at this location. This arrangement is generally used in the rocker arm of the overhead walls of IC engine, bell crank lever in the railway signal mechanism, and levers of the hand pump. Then second arrangement is there. Okay, where the fulcrum is being shifted. Here the fulcrum is available at this location. Fulcrum is being shifted towards the extreme left end. Okay, now this is the P force and F is there. Okay, load arm and efforts arms are being shown. Now still the mechanical advantage is greater than 1 because L1 is greater than L2 is there. Now this arrangement is generally used in the safety valves, lever loaded safety valve. Now third arrangement is there where L1 is less than L2, where mechanical advantage is less than 1. You require more efforts to lift the load. Therefore this type of arrangement is generally not being used in the mechanical applications. Then next one, how to design the levers. These are the different types of lever, brief introduction, and different nomenclature we are studying. Now we will go for how to design, how to evaluate the dimensions of the lever. It is easy to design the levers. Initially, the length of the lever is decided on the basis of the leverage required, and cross section is being determined based on the bending stress. Now let us see what are the different design processes are there for the forces. Now let us see the load arm and efforts arms are there. Then load and efforts are being shown here. R is nothing but reaction at the fulcrum is there. Now by doing a summation of forces in y direction, you will get F plus P is equal to R. And taking a bending moment at this location, you will get P into L1 is equal to F into L2. Therefore P will be equal to the F into L2 divided by L1, and R is equal to P plus F is there. Now you got the two equations for the simple levers. Now if it is a bell crank lever is there, if where the forces are vertical, in those forces are inclined, in such a cases it is calculated as R is equal to under root of F square plus P square minus 2FP into cos theta. For the bell crank lever, the angle of theta will be 90 degree. Therefore R will be equal to the under root of F square plus P square. Then what type of force analysis is there? Now let us see. Now this design of a lever arm, that will consist of the calculation of different cross sections is there. Now suppose this is the fulcrum is there. Fulcrum is nothing but it is having a one bearing is there, having an outer diameter of 2d1 and inner diameter of d1 is there. Now let us say this rectangular cross section or elliptical cross sections are available. Suppose it is rectangular cross section, then the dimensions are b into d, and the elliptical cross section is nothing but dimensions of a and b. Okay, major diameter and minor diameters are there. Now maximum bending moment will occur, that is P into L1 is there. Now this is subject to this pin will be available which will support the lever arms. Now this pin will have a bearing pressure. Now it will get a bearing pressure. Now this bearing pressure will be evaluated as the force divided by the projected area, that is R divided by L into D1. Then what are the this bush is available at this location, that will subjected to the different types of stresses. Now generally whatever the bush is being used, it is from the phosphor bronze is available. Now let us see now how to evaluate the different types of dimension. Now the bending moment will be evaluated as a P into L minus D1 at this outer surface is there. Now mass moment of inertia will be equal to the BD cube by 12 for the rectangular section, and distance of N5 will be equal to the D by 2. Generally D is being taken as the 2 times of B. Therefore for elliptical section also, then I will be taken as the pi into AB A cube divided by 64, and Y will be equal to the A by 2. Now sigma B, and therefore bending stress will be equal to the M by I is equal to sigma by Y. Therefore sigma is equal to M into Y divided by I. Now value of M is known, Y is known, and I is known. Okay, now from this we can evaluate the dimensions. Then next one is nothing but design of a fulcrum pin. Now how to design the fulcrum pin? Fulcrum pin will be designed by considering the crushing stress. Now, or crushing, bearing pressure, that is the compressive stress, that is load divided by projected area, that is load is nothing but reaction and projected area is nothing but L into d1, and the shear stress available at the fulcrum pin, it will fall under the double shear, therefore 2 into pi by 4 into d1 square. Now using this we can design the levers. Okay, thank you.